Okay, kids, you can see that I have an awesome piece of wire sitting on top of my head. You might be saying, why is he doing that? You know the answer. I'm a little weird. But other than that, I wanted to show you the best physics teaching tool. Matter of fact, I call it the UTT. UTT, Ultimate Teaching Tool, right here. This piece of wire. Yeah, you're going to come to love this piece of wire. Yes, you are. But I hate it. Billy, stop it. Don't be so angsty. Come on, it's only Monday. Billy. Yeah, you're going to love it. No, I won't, Billy. Billy. So now this is going to show you and teach you about magnetic flux. Yeah, you've heard the word flux before. The flux capacitor. We all know that the movie Back to the Future is one of the best movies in the history of movies. Matter of fact, I was watching it yesterday. Just yesterday I was watching it. Sitting there going, this is a great movie. Always will be. Always was. Okay? If you haven't watched it, you're not an American. Go watch it right now. Shut this video off. Go watch. Yeah, go. Wait. Okay, back. Wasn't it awesome? Yeah, great movie. Anyways, the flux capacitor. So this, you might be saying, well, how does this have to do with anything like Back to the Future and whatnot? Okay, it's a piece of wire, right? But the thing is, what we're going to do is learn about what flux is. Flux is when a magnetic field, okay, magnetic field, remember fingers, field, right, and rule stuff? When a magnetic field goes through an area of wire. Now, my wire here is basically circular, okay? But it doesn't have to be circular. It can be a square of wire. So when a magnetic field goes through an area of wire, you have flux. That's what flux is. I thought flux was change. Like when things are in flux, they change. That is actually very good, Billy. That is true. And we're going to show you that that change becomes very important when it comes to flux. Billy, nice job. Thank you. Billy. So now, what are you, okay, so wait. So if you have any field going through a wire, you have flux. Yes, that's simple. We have an equation for it, people. We have an equation for it. Yes, it's physics. You know there's an equation for this. Of course you know that. It's physics. So flux is actually represented by the Greek letter. You ready for this? What do the giants say? Fee, fi, fo, fum. I smell the blood of an Englishman. Okay, remember fee, fi, fo, fum? Yeah, Jack and the Beanstalk. Sweet, sweet story. This is the Greek letter phi, and it is what we use to abbreviate what is flux. Now, flux is the amount of field. It's got to have field in it, right? And we all remember that B represents field. All right, and we have to have it going through a wire, an area of wire. Okay, like a circle of wire or a square of wire, whatever shape makes you happy. Okay, so that area, there we go. That is flux. Flux is strength of the field going through an area of wire. Now, we're also going to throw this in there. For $19.99, you also get, if you call now, operators are standing by. Okay, you call now, we're also going to throw in a cosine of theta in there for you. Okay, all right, okay. Wait a minute, in the equations for forces on wires and particles, it was the sine of theta. That is very good, Billy. Billy, you are on a roll today, Billy. Better than being on a bun. Billy, funny. Oh, now, that's true. It used to be, but that's not what it is with flux. Flux is the cosine of theta. Now, wait, what is this cosine of theta thing in which you speak? Okay, so let me see. Get a ruler. Okay, ruler. Okay, here's a ruler. This one's Nikita Khrushchev. Okay, Nikita Khrushchev. Okay, he's a ruler. Well, he's dead now. He was a ruler. Now, the thing is, so let's say I've got my loop of wire, and the field's going from the ceiling down through the loop of wire down to the floor. So we have some flux, right? We would multiply the strength of the field times the area of the wire. What's this cosine of theta? Okay. This represents the plane of this here is the plane of the wire. And if I put a perpendicular to the plane, okay, a perpendicular to the plane, ow, you stop spitting. A perpendicular to the plane, and I measure the angle between that perpendicular and the plane, right, that would be 90 degrees. Oh, that's what goes in there, right? No. Okay. The angle is an imaginary line. I'll use this actually for my imaginary line. So it actually, the imaginary line is actually the angle is between the imaginary line being the field. So this is the field line. The field line, and the angle between the field line and this perpendicular, which I'm holding up, is represented by the ruler. Wait a minute. Yeah. So if the field is going straight down from the ceiling to the floor, and this represents my field line, and here's this perpendicular, what angle is that? 0. That is correct. That is 0 degrees. So what if I made my field, my magnetic field, not coming straight down, but coming in here like at a 45-degree angle through the wire? Okay, what is the angle now? Well, it's between the field and, okay, hold this up. Yeah, you try this, okay? It's like skill, years of practice. I had to go to college and get a master's degree so I could do it. You should see the course I took. It's how to hold 3 things at once with one hand in your left hand. 101. Nailed it, got a 92 on the final. Boom, yeah. Okay, so anyways, this is 45 degrees. So that would be measured from the perpendicular to the plane of the wire to the field lines. So there's my 45 degrees. What if the angle were like, what if the field lines were coming in like this? And so maybe they're coming in like this, and between these field lines and this perpendicular to the plane of the wire is 70 degrees. Now I put the cosine of 70 in there. Okay, see with that angle? That angle is this angle here. Okay, angle here between the field lines and the imaginary perpendicular, which is an imaginary here because I'm actually holding something which is you're not imagining it now. Yeah. So if I could try to draw this out, I'm not good at drawing 3 dimensions. I'm good at holding things in 3 dimensions. My left hand, nail it, 92, remember? But if I were to draw, so this is the plane of the wire. Here's the wire, kind of looking at it straight. And here's your perpendicular to the plane of the wire. And if the field lines, here's your magnetic field. Here's some field lines representing that magnetic field. If these field lines are at a 70 degrees, okay, maybe 70 degrees, making up, I don't know what it is. To the perpendicular, that would be the cosine of 70 would go in here. Okay, now can we see what's going to happen? Let's do a little bit of math. The flux is going to be maximum. Okay, maximum flux capacitor, 1.21 gigawatts. Okay, if you're going to get that maximum flux, you want this angle here to be 0. Angle 0? Well, why would you want the angle to be 0? Because look, you kids know, you all know, maybe, I hope, and maybe not, cosine of 0 is 1. All right? And we know then the cosine of 90 is 0. So the cosine of 90, now 90 would be, if we have, here's my loop of wire, here's that imagine that's the ruler I was holding up, right? So here's my loop of wire, and here's the ruler I'm holding up, like that. And if we have the field lines straight down, as I was saying earlier, from the ceiling, that angle would be 0 degrees. And that's where you get maximum flux. And that makes sense, I would hope, because that's where you get the most field lines going through the loop of wire. The most field lines coming through here is where you get the flux. Remember, that's flux field lines in the area. You get the most flux when you have that field, those field lines coming in here, perpendicular to the plane of the wire or parallel to, in this case, my ruler. Okay, so the imaginary normal is actually the normal to the plane of the wire. And so when you have that, you put a 1 in here and you get maximum flux. Now, what would happen if we had our field lines? Okay, like this. Here's the field. So we've got our field like this, coming from the right to the left, and we have the wire here. And so now the field lines are doing this. Well, no field lines are going through the face of the wire now, are they? Yeah, so if you've got you're holding the wire like this, there's no field lines going through there. You're not going through the face of the wire. So how much flux you're going to have? You don't have any field lines going through the face of the wire. 0. And that is 90 degrees. Okay, that's 90 degrees. So that would be a cosine of 90, which we all know is 0. And you would have no flux. Okay. So that's how the angle works. Now, usually what you want to know is maximum flux. So usually most problems will have this as being a cosine of 0, and therefore not even have to think about it. So that's what we're usually dealing with here, but we do occasionally have some problems we have to solve that have an angle. And so the field lines are usually doing this, going through the face of the wire. Okay, right there, nice and perpendicular to the plane. But sometimes we have them going through like this, and that's where that cosine of that thing comes through. And remember, that angle is going to be the angle from the field lines zoom, up to that perpendicular to the plane. All right, so that's what we have. Now that's flux. When we multiply this out, where's my marker, man? Where's my marker? What I do with my marker? I really don't know what I did with it. I don't know where it went. I don't know. I'm a mess. All right, so we'll go with red, okay? A little festive colors here, a little red and green. And so this unit is called the Weber, and it's abbreviated by WB Mason, okay? WB Mason. Oh, funny. And that is the unit for flux. All right, that's a little quick thing on flux and differences in the amount of flux. All right, and we'll come back to that real soon. All right, talk to you soon, kids.